Пускайте. Так, у нас по-английски сейчас. Да? Ну что, можно?
Да, вот это пишет.
Пишет. Все есть, да? Okay, good morning, everyone. Our first talk for today is by Andrei Vesnin. He will speak about right angle knots and beams.
Thank you very much. It's my pleasure to present talks related to quandles and groups. And mostly I will talk about hyperbolic geometry and hyperbolic volumes. So I will follow the following way. First, I reveal some basic things about hyperbolic geometry. Next, I would like to present you some conjecture about hyperbolic knots, which call it now right-angle knot conjecture. And after that, I explain how you can verify this conjecture of some cases using a volume approach. So, since our conference is not about hyperbolic geometry, I would like to reveal something very basic things. So, why we consider hyperbolic geometry when we talk about three-dimensional manifolds. Firstly, because of geometrization theorem, firstly, it was geometrization conjecture by Thompson and finally proved by Herman. So, conjecture said now theorem says that the interior of very compact three-dimensional manifolds can be canonically decomposed in geometrical pieces. What means geometrical pieces? In this context, it means that you consider one of 8 possible geometrical structures. Some of them are very known, Euclidean, spherical, hyperbolic. Also, there are 2 product geometries and also 3 so-called exotic geometries corresponding to universal cover of a set of A, near geometry, solvable geometry. And most of research about free manifolds, about geometric free manifolds, devoted to hyperbolic free manifolds and rings. So why it is so important? Because of the following most of rigidity theorem. If you have 2 hyperbolic manifolds, and if there is isomorphism between groups, then the theorem says that, there is a isometry between these manifolds. So, the corollary, we immediately obtain that any topological, any geometric invariant of these manifolds is also topological invariant. Particularly, I will be interested in volume of these manifolds. And I am going to consider knot complements as a three-dimensional hyperbolic manifold and consider volume of these manifolds as a topological invariant of knots. And just recall you what is hyperbolic geometry. So you can think about, if you look on a dimension 3, so you can think about the upper half space model with such a magic element, and the group of adaptation isometries is isomorphic to P0 to C, and any element of this group acts on hyperbolic space in the following represented way. If we think about points as a quaternions with a complex path. Okay. Okay, so you can see the point as a pair, as a complex number Z, and positive key as a part of quaternions. And you can see the quaternion action, and you obtain action in 3-dimensional space by this linear fraction transformation. Yeah. Okay, so just for imagination, the picture. So if you think about the upper half space as a model of hyperbolic geometry, so geodesic planes are just semispheres, which are orthogonal to the basic space, basic plane, or just vertical semiplanes. And if you're interested to calculate volume, it is not so easy, and this classical result firstly by Lobachevsky and then by Miller. So Miller some sense modifies Lobachevsky approach and obtains the following result. So suppose we have a tetrahedron in hyperbolic three-dimensional space. such that all its vertices belong to the boundary of the space, to the absolute, and you can draw the 3 points belong to the plane, and the fourth point is at infinity. So if you consider such tetrahedron, so it's easy to understand that the sum of angles alpha, beta, and gamma equal to pi. So it's just a usual Euclidean triangle, and everything determined by these angles. The opposite angles are the same as the angles that point to opposite h. And Milnor formula says that the volume of such a manifold, such a tetrahedron can be found as a sum of 3 Lobachevsky functions calculated in this alpha, beta, and gamma. So we have alpha, beta, and gamma, 3 Euclidean angles, and some of them include pi. So here there are only 2 parameters, and it's easy to understand when you can obtain the maximal volume. You obtain maximal volume of ideal means with all versus infinity tetrahedron if all angles equal to pi over 3. So in this case, we have really something like 1.01 and so on. It's constant, which you usually use with P3. This is the volume of maximal possible tetrahedron in hyperbolic space. And this is the Lobachevsky function, which we use to calculate the volume. It's kind of a logarithmic function. It's theoretical. And now let's return to knot theory and consider knots. So from the generalization theorem, it is the corollary, which was closely conjectured by Robert Riley. It is corollary about knot complements, and the statement says that if you have a knot, then its complement has the geometric structure. If you don't leave, it is not satellite knot. And in this case, there are 2 possibilities. Knot can be torus knot or hyperbolic knot. So if you want to introduce hyperbolic structure, people very often do it in the following way. They present complement of the knot as a union of hyperbolic polyhedra. In this case, you just take two ideal tetrahedra. So these points are removed and glued according to these errors. It's quite famous construction, so I don't want to discuss in details. So if you want to obtain hyperbolic structure, it is one of the possible ways. And what I want to discuss today is some relation between polyhedra and knots. And I would like to present some construction due to Hermitian and Rubinstein, quite old construction. And this is related to coloring. So suppose we have a plane graph here. So these are regions of this graph, and so we assume that this is planar graph, and also each vertex is 4. So there are 4 regions which meet in one vertex, and we can consider coloring into colors similar to the chessboard. So just use white and black color. This is one possible example. And sometimes people use colors, sometimes plus or minus. It's about the same. And this construction leads to obtain a complement of the length, and you can draw this length. So you just consider alternating case, and you start from such coloring of the 4 planar graph, and as a result, you obtain length, something like that, starts with the edges, and more precise construction the following. So we can take 2 copies of such a polyhedron. So this graph is the skeleton of polyhedra, and 1 copy is known by gamma. Gamma is the graph by the polyhedra plus 1 copy, and we consider this polyhedra with the faces colored in 2 colors, similar to the chessboard, and consider another copy where we inverse color. And the rule is green. The green rule is the following: we consider some face of a polyhedra of first polyhedra, and we glue it with similar face of second polyhedra, but during the green we use some rotation. So if you just identify faces by identity transformation, we obtain again the sphere. But we use some rotation in the face, and if you have a face with ni edges, so we use such rotation where sigma I is plus or minus, so it's define the direction of rotation. So clockwise or counterclockwise. So we obtain something, and the result is we obtain a topological space, firstly denoted by m gamma bar. And if you denote all vertices, you can see the situation when all vertices belong to the boundary of the space. We don't consider them. So if you consider this minimally fold with removed vertices, then the result is that this manifold is canonically homeomorphic to the link component. Okay, so you can see the polyhedron like this one, and you can immediately see the ring. The ring complement obtained from two copies. And green rule is described by color. And this is definition according to Chipin-Hart, Kaufman, E. Arthur. So they call it ring right-angled if you can decompose the complement in right-angled polyhedron. And two very famous examples of rings, for example, White ring and Borromean rings, both of them are right-angled. It's a known result. You can obtain White ring complement from one of the copy of right-angle octahedra and Borromean rings from two copies. And I'd like to present some picture, very nice recent preprint on top. It's known, everybody knows how to do this kind of folklore, how to do it, but he very carefully draw pictures. I would like to send pictures. So we start with two copies of polyhedron. This is just octahedron. And you have one copy with plus minuses and another copy with opposite signs, plus or minuses. And you start to glue one region with another one and with some rotation. And you have edges, and edges split in classes of equivalent under this gluing. And this equivalence presented by colors below picture. For example, you can consider the, for example, green edge is belong to the region A. So A has a class. So you can see the rotation when you glue with another class of A. So you have 2 pi over 3 tone, and the image of this green edge will be here. After that, it's belong to the region D, and D has a class, and again you glue back and obtain and so on. But if you want to obtain a complete geometric structure, we need to verify that some of the angles which associated to edges from the sum equivalence class give us pi over 2 pi. So we want to obtain the good neighborhood, so we want to obtain 2 pi. So you can see here all classes has only 4 elements, just by construction. And you see that we have totally 2 pi divided by 4, so we can start with octahedron with the other angles pi over 2. And in this case, we obtain complete structure. In general, you can start from arbitrary polyhedra and you obtain something, you cannot show that you use right angle. This is the problem. And this example very, very nicely, everything's achieved here. And the conjecture formulated years ago by Chipin-Hart, Ilya Kaufman, and Jessica Parson, they considered this question about construction of links and knots complements, and in the conjecture there are no right-angled knots. So all right-angled links have more than one component. I presented you examples with 2 components and 3 components. There's some procedure how to do it, and why this conjecture appeared. In some sense, it's appeared because of volume calculations, and I would like to present you some simple calculations up to for knots up to 8 crossings. So they did it up to 11, but it's more technical, and they want to visualize. So I present on discussion up to 8 crossings, and I will use volume arguments. So now about volumes. So we consider polyhedra in have a volume space, and what we want to have, we want to have ideal vertices. So always this infinity n, and there are angles by which, so I see the ideal rectangle polyhedra. And also result obtained by Andreev give us characterization of corresponding skeletons, and the theorem, just particular part of more general theorem, say that the rhetorical polyhedra admit realization as ideal rectangular polyhedra in hyperbolic space if you don't leave. It is four-valent, so each vertex has four adjacent edges. And there are no non-trivial fourth circuits. So if you look at all the surface of the polyhedron, and you can see the closest curve, so this curve intersects at least four edges. There is only one trivial exception. This is when this curve is around vertex. They call it trivial. And just from early formula, we can either observe that commutatoric of this polyhedra is like this one. So you can calculate number of vertices. You can see relation between number of faces, number of vertices, and you see that there are always at least 8 triangular faces in such polyhedra, just from early formula. So the simplest one is the hidden, which we already discussed. And if you have another faces, you'll get many triangles in subtractions. And I want to give you some examples. And this family, ancient family of polyhedra, and all of them look as an antiprism. You have angle top and angle bottom, and two levels of triangle between them. So the first guy is just a polyhedron, and you can see the rule. So let me call it antiprism. And number means number of faces in top and bottom angle. This polyhedra appeared in famous third selection notice, for example, figurated volume. So he obtained the following formula. So volume such a polyhedra just to n some expression in terms of Lobachevsky function, which we already discussed. And if here in your case of octahedron, the volume is some constant which usually denote V8 is 3 something. And fortunately, we can explain how to construct the new polyhedra from our family using H-twisting transformation. So let's consider the part of the face. So there are 3 edges, E1, E2, and E3. And let's consider H-twisting, which is the following. You take H1 and E2, you remove them, but you connect the terminal vertex by with the new vertex V. So the H-twist, that's just transformation from T to T star. It's local besides some phase. And as described, how we do it, we delete the edges, we create new vertex, and we connect new vertex with the terminal. So this example, we can apply a transformation here because we need at least 4 bond to apply this transformation. But if you have 1, you can do it. For example, for this polyhedra, you can use this E1 and E3 and apply transformation. You obtain the polyhedral. So we have a family of antiprism in this transformation. And next statement devoted to special kind. If you apply such transformation to the antiprism, you obtain something new, which we call it twisted antiprism, and also we are able to calculate volume in terms of Lobachevsky function. And since in Hauger geometry, everything is determined by combinatorics and diagonal angles, I mean everything for polyhedra, because of rigidity theory, we already fixed diagonal angles. So all angles pi over 2. So now everything depends just on combinatorics. So it's natural to ask if you can estimate any geometrical parameters in terms of combinatorics. And for example, it was done by Christian Atkinson. He obtained lower upper bounds for the volume of polyhedra, which has F faces. If you have polyhedra, right angles, hyperbolic, ideal, in hyperbolic in space, so there are low bounds, there are constant V3, and upper bound are constant V3. And equality calls for the hydron. And the first guys with 8, 9, and 10 faces are known. I mean, there are no guys for 9, but for 8, you know. And if you start from 10, so you improve a little bit this bound, at the bound, so it was -6, so we can show that -7. So I show you how it looks. So these volumes are corresponding polyhedra and this lower on the bottom. And so we discussed antiprism and twist transformation. So net result is due to people from graph theory, Brinkman and his colleagues. So he considered the same family of graphs, and they proved that you can obtain polyhedra from our family, so ideal rectangle, from antiprism and HT smooth. So any polyhedra is either antiprism or obtained from antiprism from some family, some finite number of H-twists. And recently, Nikolai Verkhovets improved this result. He observed that you can obtain everything from A4. Not from AN here, but it's just all antiprism and it's about one of antiprism and the guys that we obtained by H-twists. And this is picture how the volumes grow up. So you have, if you move, can you move a little bit? So here green means antiprism, yellow means twin antiprisms, and all other can obtain from them. This three show you how they grow up. And we were able to calculate volumes up to 23 faces. You see, you can consider 23 faces, for example, you have more than 72,000 of polyhedra from our family, and among them not so many different volumes. So only 13,000 of different volumes, and the minimal volume like this one, and it's much more. So we calculated some modification of Jeffrey's formula. Of course, these are just approximation up to 6 digits. And this picture I showed you, and if we discuss equality between complement, this obtained from A3, so this means the smallest volume rectangle here. So we use the smallest polyhedra. And also we see that there are some description of polyhedra with volumes at most 5 V8. We enumerated all these volumes, so you know the volumes of all polyhedra up to. And this is just initial list, so it's the hedron, this guy 4, this guy obtained by H3, the guy 5, not the guy and so on. And now about the right-angled knot conjecture. And I just recall you the picture of knots, which I really like. So in this picture from paper about molecular knots, they indicate about color different properties of knots. For example, torus knot depends on red, and so color explains some properties of the knot. So we can see the hyperbolic case. We are interested in hyperbolic knots. Of course, these knots are well studied, and there's many papers about volumes of them. For example, there is a program, Snappy, where all these volumes can be created. So what we know about volumes? In hyperbolic case, we start with figure 8 knot, we know its volume and so on. For any knot from initial list, you know its volume. It's presented on the left, but at the same time, we know volumes of polyhedra. They presented on the right, and just for convenience, I use it blue color to show all volumes which are at most 7.32, twice the volumes of polyhedra. For polyhedra, there are only 3 such guys, and for knots, only this family. So you can easily compare, you cannot obtain knot complement from such a polyhedra just because of volume. So this simple approach, how to understand that there are no right-angled knots in this class, and Mikhail Kaufman and Poncelet observed this approach and they applied it up to 11 persons. Of course, it's for initial list, and we don't have for the moment idea how to prove it in general. There are some support of the concept. So this example of how you can apply results about volumes of polyhedra in knot theory in this model. Property to be commensurable with right-angled Tomsk group is very important. So if we are in such knots. And another topic which I want to discuss very quickly about the connection of volumes calculation for right angle polyhedra and maximum volume conjecture. I recall very briefly what is the volume conjecture. Let's consider to write Ferro invariant of free manifold. I am not going to define it now. It's another talk. So just consider to write Ferro invariant of three-dimensional manifold, and I'd like to formulate a conjecture following Cheng and Yang recent paper. So let us consider three-dimensional symbolic manifold as a closed or discussed or common with a geodetic boundary. So all of this possibilities are okay. And we calculate to write Ferro invariant with parameter R. I mean, we calculate to write Ferro invariant in the point, it's point of 2 pi I over R. So we calculate these numbers and we take logarithm and take a limit when R tends to infinity or along all natural numbers. A conjecture in this case is that you obtain the limit volume of this manifold. It's about hyperbolic. So on left we have combinatorial description, which related to right real construction, and to the right we have hyperbolic volume. It's there are many modifications of this conjecture. Some of the first version was formulated by Kashaev. So people start from Kashaev volume conjecture, but there are some progress, not some, big progress. And similar version for the ring complement can be formulated like this one. So again, you consider to write Ferro invariant for the ring complement, and on the right, the limit you obtain the constant volume of tetrahedron. The free is just a constant which I presented before, and another multiplier is the so-called simplicial volume of ground floor. If your link is hyperbolic, it's just a volume. And the conjecture quality for nodes when it's norm equal to 0, so not hyperbolic. And one of the recent results is due to Vermicelli, Pagani, and Yang. And they observed if your link is a figure 8 node of Riemann rings. So this expression on the left, let's give you, it can be transformed into expression in terms of a Jones-colored polynomial. And on the right, again, you have volume. So some volume conjecture formulated in terms of colored Jones polynomial, some of terms of to write Ferro invariant. This originally from for manifolds, particularly for rings, and another version due to Konstantin van der Wee for planar graphs. So let's consider equivalent plane graph. So just skeleton of polyhedron. We consider just such polyhedron, and again calculate version of to write Ferro invariant for graphs. Define, but you can follow the paper. So let's consider such a to write Ferro invariant and calculate it in special exponents, and again take the limit. So conjecture is you'll get as a limit, you'll get supreme of volume of such a polyhedra. So it means you consider you have a graph and you consider all polyhedra for which this graph is scalable. So you fix combinatorials. So, and you can change the angles. So you consider maximal volume for such a family. And this is the conjecture. And just a few months ago, I remember in February, it was published in Transactions of American Mathematical Society, paper by Delecki, and he considered this limit, I mean, this expression on the right, and he proved the following theorem. So if you consider skeletons of polyhedra, so frequently the graph, so the supreme of this volume is just volume of polyhedra, which he called it rectification. If I would like to explain maybe that I have to 1 or 2 minutes. One last one. Yeah. So what is this? So you start with a graph, and you can think about the model of Lobachevsky space in the ball, and you put in the ball in Lorentzian space. So that's in the exterior of the ball. And you can start from tetrahedra, and you can expand it, and you can go out of the ball. You'll get something which is not hyperbolic, but still some polyhedron. And what you consider, you can this ball and use consider four polars for the vertices which are outside, and you consider truncation of these vertices. So you have vertices out of the model of Holochevsky space, but you have polar plane, and you consider polyhedra formed by these polar planes. And example can be understand for this one. So you suppose you have a tetrahedron. Suppose this circle is just a boundary of then boundary of this ball. Then you can have a parabolic model, and some vertices are outside. So instead of vertices, you consider polyhedra with vertices outside. You consider truncate. So you truncate all these vertices. For example, if you truncate all vertices for tetrahedra, you obtain such truncate. These triangles can form truncations. Of course, when you truncate, you obtain the angles by 2. To obtain some polyhedra, which are and you continue this process, and finally, from this guy, you obtain such truncate when two triangles meet. This is the limit position, and for tetrahedron, it will be octahedron. So this rectification of tetrahedra will be octahedron. I mean, now you are in the model of Holochevsky space, and you can talk about parabolic volume. So it's ideal rectangular polyhedron because the vertex belongs to the boundary, and all the rectangular parallels. So again, our guides. And you can look on volumes depending on the angles of a triangle. So for pi over 3, you have a regular situation. After that, you move the vertex out of the model. So you consider truncated case. And this is the situation when the other angle are pi over 2 for truncated guy. So it's exactly octahedron. So volume. And finally, I want to relate everything for the volume projection. So what we have. For example, if you have pyramid, pyramid, you can consider truncation of different polyhedron, but combinatorically it's just a median graph. So if you have a blue prism, you consider its rectification, it will be the black, it will be just anti-prism is number 5. And of course, you can do inverse. Starting from polyhedra, which is ideal rectangle, you can obtain the original. So now, what we have now, we understand the structure of ideal rectangle polyhedra and their volume. So I can say that now we know the right side in the volume conjecture. Thank you very much.
Are there any questions or comments?
Can you say something about groups of right-angle links? Do you know some connection of this group with right-angle arc?
I don't think
So it's different type of right angles.
Yeah, yes.
No, but somebody studied it.
I can explain maybe privately, not construction. You can start from Foxter polyhedron with ideal vertices and angles pi over 2. And you can see the Foxter group, still the right angle Foxter group. Okay. And I can suggest you some two coloring of the faces, which give description of the kernel of index of the homomorphism. So you can see the subgroup of index 4, the Foxter group, which is a fundamental group of the manifold with cutters.
It's subgroup of Foxter.
Of index 4. In some cases.
In some cases.
Yes.
It has torsion.
No. Subtorsion.
Foxter.
It's
But subgroup of index 4 also has torsion. Sorry, maybe.
It's kernel of some common.
Kernel of some.
There is some Foxter group and some common field, and it's kernel with torsion 3 to the middle group of the lead constant. But it's not possible, not all possible cases, just one way.
Any more questions? Then thank you very much. We resume in 4 minutes.
А что, посчитать, посмотреть там же, для Бронеевских, для всего известно, группы глянуть, поэтому все вы какие-то не оказаться ирокезами. Поэтому Вань там я говорю так, почему разное? Ну, что группа есть представление какое-то, а может быть, его можно представить других порождающих составить.
Нет, вот может взять, например, то же самое какая-то. Может взять раскраску 20 цвет. Ну, не так клеить, как эти ребята предлагают клеить, а просто эта раскраска будет тебе давать абсолютно нет группы.
Ну да.
И ядро этого будет бесключение.
Ну, тебе и надо, чтобы без исключения.
Да, оно будет бесключение. Потому что не все вот могут сказать.
Все пауза. Интересный вопрос. А какие группы, у каких зацеплений группы являются ракеты?
А вы поставьте мой докладик.
Бывает, берите эти тривиальные зацепления. Нет, я понимаю, что по-другому. Так, а где-то дневников.
Есть. Не время. Есть очень хорошо.
Может, надо попросить выключить? Может, попросить этот кондиционер?
Я не знаю, ну, тут пойдем, еще.
Да, включите.
Температуры нет. Температуры нет. Не чихаю. Не, ну я вакцинирован, что ты боишься. У меня внутри спутник, я уже улетел.
А между прочим, те, кто вакцинированы, они не распространяют.
Я знаю.
Даже есть некоторые высказывают мнение, что они более опасны.
Ну, это я знаю. Ваше мнение.
Не мое мнение.
Ваше мнение ковидных диссидентов я слыхал.
Нет, я вчера читал тред под этот самый там под заявление Бондова.
О, Леша, что ли?
Нет, да, про Бремзена, про смерть Бремзена. Там такой холивар, я его вчера как раз вечером прочел.
Леша Бондал, а Бремзен это кто?
Бремзен. Ну, это бывший замдиректора писательской школы. Он когда-то...
Да. И Леша написал, что не Полок?
Нет, он написал, что общественность скрывает, что его убила прививка.
Леша, он известный, так сказать.
Да, я вчера согласился. Так, давайте, сконтинируем.
Да, слушай, мы тоже распространяемся, а нас записывают.
Да. Нет, я передал то, что лежит в открытом доступе.
Let's continue our session. Our next speaker is Mikhail Mishidin. He will speak about some skew braces constructed on three groups.
At first, I want to thank organizers of our conference to take part in this conference and make reports. And then start. The name of my report is the some skew braces constructed on three groups. At first, I want to give some known definitions and formulate some known results, and after I give very particular answer on the next question: what the structures of skew braces may be if additive group is effectively a Billiard group? But first, Ram in 2007 introduced new algebraic system, and name is brace. Brace is an algebraic system with two operations, plus and circle, such that for every operation A is a group, and this plus it's a Billiard group, and this operation connected by the axiom of brace with the next form. In some sense, this algebraic system is not new. For example, in the lectures of Kurosh, 1974, you can find the next example. If I is some important ring, with operations plus and dot, then we can define new operation circle. It's named adjoint multiplication by the next formula. And it's not difficult to check that left and right part of axiom of brace is the same. So we have for every important ring or radical ring, we can constrain algebraic system brace. Maybe big interest in such an algebraic system started from the question of Winkel, 1990. He asked the next: may be interesting to study the theoretical solution of Young-Baxter equation of the fourth law. And he gave two examples. For one of them is the next. If R of x and y is the operation the next form, x is fixed, and in the second part x circle y, where circle is some operation, then from Young-Baxter equation we obtain that circle defined algebraic system is known as rect. If we add some adding relation, we obtain quantity. And after this paper, the problem studied that theoretical solution was investigated by mechanicals. Some of them insist this. If you can rewrite Young-Baxter equation in the next form, as long relation in braid group, then Rump observes that a classical brace produces an involutive non-degenerate solution of Young-Baxter equation, which of the next form is this formula. The next generalization was given by Guarnieri and Legrabin. They defined a left skew brace as an algebraic system with two operations, dot and circle, such that A with every this operation are groups, and they are connected by the axiom of skew brace on the next form. The group A with dot is additive group, and the group A with circle is multiplicative. If A with dot is a billion, then that is a classical brace introduced by Ram. Maybe the main property of axiom of skew brace is the next. If you take axiom of brace, the next form, and rewrite it in equivalent form, then we obtain that we have map lambda from A with circle the group automorphisms of A with dot of the next form, and its map is a group homomorphism. And from this we obtain all properties of skew braces. If also for brace, if you have skew brace, we can obtain solution of Yang-Baxter equation of the next form. Maybe more difficult, but it's the same. Also, we can define by quandle, and other algebraic system. For the finite set A, we can find all group structures on skew based. If you take of the pairs of structures matches by identity of skew base. And some examples of calculations I take from this paper of 3 authors. First, n is the order of number of elements of A, B of n is number of brace structures, C, S of n, number of skew brace structures. It's interesting that this table contains some questions. For example, for number 64, it's unknown number of brace structures and also number of skew brace structures. If A is infinity, then number of group structures on set A is infinity. Therefore, it's necessary to consider other ways of finding consistent structures. And I think the main result in this direction obtained Guarnieri and Vinravin. They obtain characterization skew-left braces in terms of regular subgroups of Golomov. So if you have some group, then we define the Golomorph group. It's a split extension of both A and A with the product by this formula. Any subgroup H of Golomorph X on A by the next ruler. And main definition subgroup H of Golomorph is regular if for each element of A there exists a unique pair from the group subgroup H such that X multiplied F of A is equal to 1. It means that action of H on the set A is exact and transitive. And the description contains in the next results. Lemma, let A the group H is regular subgroup of Golomorph, then projection H on the second component is bijective. Theorem let A be skew-left brace, then the next set lambda of A, A from A is a regular subgroup of Golomorph. Conversely, if A with dot is a group and H is regular subgroup of Golomorph, then A is skew-left brace with this operation so-called defined by the next formula, where F is a first component of pre-image of element A. P by this index 2 is bijection by the lemma. And proposition give classification of skew brace structures. Let A be a group, there exists a bijective correspondence between skew-left brace structures over A and regular subgroups of Golomorph. Moreover, isomorphic skew brace structures over A corresponds to conjugate subgroups of Golomorph by elements of all A. Note that if we have skew-left brace, then the map from G with circle to OG with dot is group homomorphism. But if we consider lambda as a map from G with dot to O with dot, its may not be homomorphism. And last year we gave the next definition. A skew brace is said to be lambda homomorphic skew brace if the map defined by the next formula is homomorphism. And last year we proved the uses prove the next theorem. Let G be group lambda bigger morphism of G into the group automorphisms. The set H with lambda, the next form, is subgroup of Golomov if and only if this set is subset of kernel lambda. Moreover, if H lambda is subgroup, then it's regular, and it means that we have less cube brace where circle is defined by the next formula. And we prove that this inclusion we can check only for generators for group G. More exactly, the next theorem. Let G be group generated by the set X, XY, and lambda the morphism such that if we have such inclusion, then the inclusion for every AB of group G. And in the second part of my talk, I want to give some particular answer on the next question. What kind of cube braces may be constructed on the free group F with total or equivalently? What kind of groups F with circle may be in the cube brace which is constructed on the free group F? And I use the main property of free groups. If we take free generators, then every map for generators may be continued to the morphism of Fn2 over Fn. So we have free group with generators, Golomorph with this multiplication, fix some biomorphism, and consider subset the next form. This set is a subgroup of Golomorph, this multiplication circle, if and only if we have this equality for every AB of the next proposition is true. This proposition gives some examples. Let theta be some automorphism of Fn defined on free generators by the next theta is composition commutation of generators and multiplication some elements of commutator. Or theta is composition of commutation of generators, inversion and multiplication of some elements of commutator. And this condition theta square is equal to 1. Define lambda by the next formula. All generators go to one automorphism. Then we have it's not difficult to see that we have this equality, and it means that we have a regular subgroup of Golomorph. And it means that we have a structure of left cube brace. Example 1. Let sigma arbitrary commutation and theta automorphism the next form. Commutation generators. Then it's a regular subgroup. So we have left brace structure. Let theta arbitrary e automorphism of Fn. Then it's regular subgroup. In particular, we can take arbitrary in automorphism of free group Fn. It's well known that the braid group Bn may be considered a subgroup of all the Fn, and for every element of every braid, we have this equality. Then the map lambda defined by the next formula define regular subgroup. So we have structure of squiggly brace. Note that not every automorphism of theta of free group and homomorphism lambda with the next form defines a group of Golomorph. For example, if we define theta by the next, all generators are fixed and first generator goes to x1 multiplied x2. Then we see that this equality. In the right part, not identity, and it means that H lambda is not a subgroup of Golamov. Example 6. Let's first I give some examples for free groups of rank 2, and at the end I give examples for arbitrary free group of finite rank. Let F2 be free group with free generators x1, xy, theta is automorphism the next form, permutation, lambda maps xy to automorphism theta. Then we define H with 0 kernel of lambda. It's a free subgroup of rank 3 and has three free generators. Define structure, define new operation circle by the next formula. And from our results, we obtain the algebraic system with the operation, which is a skew-left brace. And interesting that in this case, F2, the set F2 with operation circle is a free group with free generators x and y. So we have such isomorphism, but this pure left brace is non-trivial. Next example, if you take theta inversion of generators, lambda of the same, define kernel with the same generators, define operation circle by the same formula, we obtain skew left brace, and in this case, the group F2 with circle is a split extension of free group of rank 3 with cyclic group of order 2 with these regulations. May be interesting to consider inner automorphism. Inner automorphism, eta, defined by this formula, is a conjugation by element y, lambda of the same x and y go to eta. Then we define kernel of lambda, kernel defined free generators, which have the next form, z is index m. M is arbitrary integer. Then we take element S is a pair eta y from H lambda, and we have the same the next action of S on elements on free generators of the kernel lambda. It means that F2 with operation circle is a free group of rank 3. So the additive group is a free group of rank 2, and the multiplicative group is a free group of rank 3. Maybe I consider more general example. Let Fm be free group with generators x1, xn. Eta is automorphism permutation of generators, and we take lambda, map all generators to this automorphism. Then we define H0 is a kernel of lambda, which defined by the next formula. Logarithm is defined as usual. It's easy to check that we have this quality. It means that H lambda is regular subgroup of Golamov, and then using Rademacher-Schreier method, we find free generators of H0. This subgroup generated by the element Z, G, and Y, where indexes K, G, I from the next set. Then we find action of this element at x1 on the free generators of this free subgroup, and calculate nth power of element S is not. This power is non-trivial element of the free subgroup H is 0. So we have Fn with separation circle is a product of free normal subgroup of rank n squared minus n plus 1 and infinite cyclic group Z with generators S. I know that this product is not a split extension. It may be proved that Fn with separation circle does not have any torsional elements. And from a well-known theorem proved by students and Sven that a finitely generated free group without torsion admitting a free subgroup finite index is free, we obtain that our multiplicative group is free group of rank n. And I know that skew-left brace is non-trivial. So we have first additive group and second additive group are isomorphic and free non-abelian group. And structure of skew-left brace is non-trivial. And last example, let Fn be free group with generators. Fix some W from Fn, define theta in automorphism is conjugation by this element W, and take lambda the next form. Then we define kernel, define check that we have this equality. It means that H lambda is regular subgroup. Then define free generators of the kernel lambda. They have the next form. K is arbitrary integer and G is from 2 to n. Take element S from the next form. Write our word W in the next form, where W is from kernel lambda. Then we obtain that Fn with separation circle is a split extension of free group of an infinite rank F infinity and infinite cyclic group with this generator S0, which is equal to S multiplied W0 at the power minus 1. And we have such action. So we see that action is only shifted by index K. And if M is not equal to minus 1, then we obtain the Fn with separation circle is a free group of rank A, which is equal to m plus 1 multiplied n minus 1 plus 1. If m is equal to minus 1, then you have direct product of infinite, of free group of infinite, right, and infinite cyclic group. And corollary for every natural number, and there is a homomorphism lambda from F2 to out F2 such that for corresponding lambda skew brace, we have an isomorphism. The multiplicative group is a free group of rank n. And I want to give some definition and maybe formulate it, maybe interesting question. We say that two groups A and B are elementary S2 equivalent. S2 is conceived from skew brace. If and only if there is a skew brace G with operation dot and such that A and B or additive and multiplicative group or another multiplicative or additive group. And we say that two groups A and B are the equivalent if there is a sequence, maybe sequence of groups such that the groups GK and GK plus 1 are elementary as equivalent for K from 1 to n minus 1, and A each is equal to G1 and K is equal to Gn. it's not difficult to see that this relation is equivalence. And I want to move over the next problem. Let G be some group to describe class as the equivalence of group G. I suppose that for some groups, this problem may be solved. For example, for finite group using computer programs. If somebody can calculate how many brace structures, two brace structures, I think it's more difficult to find number of classes as the equivalents. Note that class SB equivalents of free group F of rank 2 contain all free non-abelian groups of finite and countable rank. And the next question, is it true that if group G is SB equivalent to the free group F2, then it contains free non-abelian subgroups? Or another words maybe says, if you start from free group of rank 2, after some steps, can we obtain a group without free non-abelian subgroups?
Questions?
Yes. Could you say if this approach is sufficient to classify all the brace structure?
Yeah, I think
Symmetric groups or for the affine line is applicable to this case?
I think this approach allows now how to find only some few brace structures. Because how to describe all regular subgroups for Gromov, it's a problem. This approach allows to take only some part of regular subgroups.
But for the symmetric group, Gromov is just the cross product of itself.
Yes, for symmetric group, Gromov is maybe direct product. Yes?
Cross
product. So, yes. But maybe direct product because every automorphism is inner except one case. Maybe, but I don't know.
No questions? Stories? But let us have to speak again. We've got 21 minutes for break.
Ну, кстати, мы работаем.
У докладчика написано по-разному. Да?
Не пойдет.
Да, я не знаю, что докладчик.
Значит, камера вот туда.
Ага,
Хорошо. А, я должен тут встать, да?
Вот, да, вот, да.
Так, ну что, готовы все?
Слушай, а может там где
Можно начинать, да? Okay, let us resume our session. Next speaker is Seiichi Kamada. The title of the talk is Commutator Identities Related to Curves on the Surface. Please.
Okay, thank you. Do you hear me?
Yes.
So today I'd like to talk about doodles and commutator identities. So first, the first and the second sections we recall the notion of doodles and virtual doodles. And in section 3, we discuss commutator identities and doodles. Here are some differences on doodles. So first, Roger Affine and Paul Taylor introduced the notion of doodles. And Mikhail Kovanov discussed doodles and he introduced the notion of doodle groups. And Ito and Taniyama discussed similar notions in the point of view of not projections. And recently, Andrew Bartholomew and Roger Affine and Naoko Kamada and myself have been studying doodles, and we made 4 papers. The first one is this one, doodles on surfaces. So we introduced the notion of doodles on surfaces and virtual doodles. And in this second paper, we discussed Gauss code description of virtual doodles. And in this paper, we gave a method to make a complete list of virtual doodles with a given crossing number. And the third paper is about coloring on virtual doodles. So abstract structure is discussed in this paper. And the last one is about commutator identities, which I'd like to talk about in this talk. Here's 3 examples of doodles. This one, and this one, and this one. The second one is called Borrowian doodles. So doodle is just immersed curves. And 2 diagrams on S2 are equivalent as a doodle if they are related by a finite sequence of R1 and R2 moves. R1 is this move, and R2 is this move. So R is Reidemeister moves R, and in the projection of Reidemeister move. So we do not the Reidemeister 3 move. This move is not allowed. Not allowed. Doodle that. Oh, yes, and okay. And a doodle diagram on a surface is generically immersed circles in a closed-oriented surface. This is the example. We have a genus 2 surface, and here is a doodle diagram with 2 components, 2 circles. And 2 diagrams are strongly equivalent if they are related by a sequence of isotopies and R1 and R2 moves. this case, we call them strongly equivalent. And two diagrams are called weakly equivalent or stably equivalent because they are related by sequence of these moves. Homeomorphism. Sigma is a surface, ambient surface, and D is a doodle diagram, and another surface and diagram in that surface. So as a pair, if there is a homeomorphism, then we consider they are the same. And R1, R2 move, and surface surgery. So, for example, this one, this is 200 surgery. We cut the surface along curve C. If the curve C is disjoint from the diagram, then cut and attach it to a pair of two disks. By this surgery, we can change the homeotype of ambient surface. In this case, we call stable equivalent. This is a relationship of doodles on surfaces and virtual doodles. Left side is an example of a doodle diagram on a surface. This is a diagram on genus 2 surface. And consider projection to the plane. Then we have some additional crossings, which we call a virtual crossing. These two crossings are not crossing in the original figure. These are obtained by considering projection onto the plane. This diagram is called the virtual doodle diagram. Virtual doodle diagram on R2. Constantly, if we have a doodle diagram on a surface and take a projection, then we have a virtual doodle diagram on R2. And conversely, if we have a virtual doodle diagram on R2, and then there is a not unique, but there is a doodle diagram on a surface. That is a realization. And virtual doodle is defined as an equivalence class of virtual doodle diagrams by these moves. These are moves. R1, R2 are usual moves for doodles. And additional, we consider 4 moves. These are virtual moves in virtual knot theory. Then there is a one-to-one correspondence between the set of doodles on surfaces, modulo stable equivalence, and virtual doodles on R2. So if we discuss doodle diagrams up to stable equivalence, then instead of this, we can discuss virtual doodles. And yesterday I have classes to teach, so I'm sorry I couldn't attend this conference. But I think there's a talk on Alexander and Marco's theorem of virtual doodles. I hope you enjoyed that talk. Now we discuss about commutator identities and the doodles. Let S be a set which we use for coloring. S is a set. And let D be a colored doodle diagram. Colored doodle diagram means a doodle diagram. Each component is colored by an element of S. This is an example. So this is Boromian doodle. This component is colored by A. And this component is colored by B. And this component is colored by C. So this is a doodle diagram colored by element S. And let N be a new system. I mean, news is this one. From the base point, we consider a simple arc and a simple closed curve, and go back to this arc. This is called news. This is a root or base point. Base point. And this point is a neck. And this loop bounds a disk. This is head. And the boundary of head is a loop of the nose. So each N1 to Nm are loops. And when we say noose system, then noose, it is N1 to Nm noose. We share the base point, and it must be ordered in this order: 1, 2, and around the base point. Then we call a noose system. This is an example. So this one is the first noose, and this is the second noose, and this is the third noose, and this is fourth noose. There are 6 nooses. If we have a colored doodle diagram and the noose system, then we have a sequence of words in S. For example, consider the first noose. We walk along the noose and turn around the loop and come back. Then this is intersection. First, we have an intersection point here, and this component is colored by B. So we put an element B, and inverse means orientation of this component. If the intersection is like this, then that is positive, and intersection is opposite, then that is negative. Here is a negative intersection, so B inverse, and we have another intersection here. This component is labeled by A, so A inverse, and then this intersection is C inverse, and this intersection is A, and this intersection is C, and this intersection is B. So we have a word. And in my notation, this is written like this: D inverse, and V. That is a conjugate of this element. And this element is a commutator. So A and C commutator is written like A, comma C bracket, and the B to the B. This means this word. Similarly, along this second loop, we have a word B inverse, C inverse, B inverse, C inverse, BC. So I will denote by BC, bracket BC. And for third noose, we have this word. And for the second noose, we have this word. And for the fifth noose, we have this word. And for the sixth, we have this word. And consider the product of these words. So that is an intersection of this loop. But this loop is homotopy to the big circle if we ignore the base point. So that means this word is identity in the free group. So this is identity among commutators in the free group. So this commutator identity is obtained from this colored diagram with a noose system, this one. here is another example. The diagram is the same. The diagram is the same. We have three components, Borromean doodle. This is Borromean doodle. And color orientation like this. A, B, C. But we change a new system. We change new system. N1, N2, N3 by this figure. First one is this. Then intersection word is first intersection C inverse, and this is B inverse, and A inverse, and B, and C, and this point is A. We have this one, and this is given like this BC inverse, A inverse, BC, A. So it is a comparator of BC and A. And similarly, for the second news, we have a commutator, CA and B. And for the third root, we have a commutator, this one. And the product must be the identity. It's free. So this is a commutator identity obtained from this colored doodle and this news system. So, of course, the colored doodle is the same. But when we change the news system, then we have a different commutator identity. This is a fundamental 7. When we have a doodle diagram, colored doodle diagram, and a news system, then we have a commutator identity. And conversely, for any commutator identity, there is a doodle diagram and news system, which is the identity. This theorem is by Payne and Taylor.
So may I ask one question here?
Yes.
Yeah, so this, when you, from the commutator identity, you are getting a doodle diagram. So this diagram is on which surface?
No, sorry. I'm discussing on S2.
Oh, I see. Okay.
S2 case. Yes, sorry. First, I recall the original and Taylor's and our papers. This paper is on S2 case. And later, I will discuss a genus, positive genus case later. But two-sphere case is essential. So I'd like to explain. I'd like to spend much time on two-sphere case because that is a fundamental.
And also, you need to choose a base point. So how do we choose the base point? I mean, will it depend on the base point or when the center of the new system?
Yes. It depends base point and also depend on the new system. And if we change the new system and base point, we discuss how it changes. That is the second part.
Okay, thank you.
So this is okay. I skipped this sheet. Here is an example. When we have this is a famous commutator identity called the whole fit identity. How to construct a doodle, colored doodle and news system using these two pages. Okay, let me skip it. And now we consider a special case of commutator identity and the news system. A commutator identity, okay, let S be a set of So first we consider a free group, and choose a non-empty subset of the free group. Or usually we consider a set first, a set S first, and consider free group. This is a usual case, but general case we can consider free group and take any subset. And commutator commutator identity is elementary on S. Elementary on S. If AI and BI is element of S, and WI is a word in S and S inverse. In this case, the commutator identity is called elementary. And a doodle diagram is colored by S. If each component is colored by element of S. And the news system is proper if every news bounds surround just one crossing intersection, and the orientation should be like this. Exactly in this figure. In that case, we call news system is proper. Then the first theorem is restated like this: a colored doodle diagram on S and a proper news system. Then we have an elementary commutator identity. And conversely, for any elementary commutator identity, there is a colored doodle and the proper news system, which is a commutator identity. So we restrict ourselves proper news system and elementary commutator identity. Then our discussion is more concrete, become more concrete. For elementary commutator identity, yes, there are 7 kinds of fundamental transformations. First, there are three transformations. First one is cyclic permutation. W1, each W1, WM, these are commutators, and we have commutator identities. And we move first commutator to the last. Then this is also obviously identity. This is cyclic permutation. And braid action or previous action or braid generator sigma j act like this. Wj and Wj plus 1 change the position. Wj plus 1 and Wj. But Wj should be conjugated by Wj plus 1. Or its inverse. Wj plus 1, Wj plus 1 conjugated by Wj inverse in Wj. That is a braid action. And the simultaneous conjugation or global conjugation. So we take an element of U, which is U, and conjugate by U means each commutator is conjugated by U simultaneously. So that corresponds to a base point change. And changing local conjugation. Let me skip these 2 moves. I don't have much time. And 6 and 7 is important. 6 is insert or delete trivial conjugate, trivial commutator, AA and U. And 7 is insertion or deletion of canceling pair. This one and its inverse. Insertion or deletion of canceling pair. That is 7. And elementary commutator identities are strictly equivalent if they are related by 4 and 5. 4 and 5. That is these moves I didn't explain. And equivalent are related by 1, 1 to 5. And weakly equivalent, all of them. And these moves correspond to geometric movement, geometric replacement of news system. So we fix the colored doodle diagram. We fix And we change the NUS system. When we have NUS system, for example, like this, then we change labeling, and the new system is 1 to like this. Then that is cyclic computation. And if we change new system like this one to this one, then we have a full width action. And this is base point change. Here's the original base point. This is original base point. And take another base point and connect to another arc by U. Then we have a global conjugation. And I skip these moves. These are homotopy deformation of the moves. And these moves are important. R1 move and R2 move. This corresponds to insertion or deletion of trivial commutator AAU. And this is insertion or deletion of the cancelling pair. So these algebraic, right side is algebraic part, and the left side is a corresponding geometric NUS system. So we have this theorem, colored Doodle diagram in this unique elementary commutator identity up to equivalence. So if we have a colored diagram D, and we don't know NUS system, any NUS system, and we have a identity, elementary identity, a proper, and we change another proper NUS system. Then we have another commutator identity, but they are equivalent. That is the first cell. And if we change D to D prime, then we need weak equivalence. Because when we change D to D prime, we apply R1 move, and R2 move. And in that case, we need these moves for commutator identities. And moreover, we can consider cobordism. Colored Doodle diagrams, we have an idea of cobordant. In that case, colored Doodle modulo cobordant correspond to elementary commutator identities. This is bijection. These are results in our paper. And now we generalize these ideas and do the diagrams on surface. So sigma G is a closely connected oriented surface with genus G, and we fix a base point. In this case, we need to fix a base point, and also we fix a cut system. Cut system means simple loops such that we obtain two disks by cut open. For example, genus 2 case is this one. After cutting, we have two disks. In other words, from the two disks, in the boundary, identifying the boundary, then we have a genus 2 surface. And alpha 1, alpha 2, alpha 1, beta 1, alpha 2, beta 2 is oriented like this, in this way. So there is a commutator, and product is 1. So we fix a cut system and base point, of course. And consider colored diagram sigma Z, and assume the diagram intersects the cut system transversely. And we consider proper NUS system. This point is here. 1, 2, 3, like Then, a colored doodle diagram on sigma 2 with a Mills system. When we fix a Mills system, then we have a commutator identity like this. The difference is this part. And if we take a proper Mills system, then this is elementary commutator identity. And what is elementary commutator identity in this form? This part is the same. Each WI is this one. This is the same. This is the same. And the right side is a new one. Left side is a commutator. And the CI and the DI is a word. Anyway, that is elementary commutator identity. Definition of elementary commutator. So in genus G case, the previous theorems are generalized to these cases. And we need some equivalence on elementary commutator identities and weak equivalence also. Then we don't need to take care of the Mills system. We can change Mills system and we can choose diagram. It's a generalization of the previous theorems. That's all. Thank you.
Thank you very much. Any questions?
Чат.
Нет,
В чате.
нет.
Ничего нет. Okay, if there are no questions, let us end the speak again. We'll see you in 7 minutes.
Thank you very much.
Oh, thank you. Thank you. Right. How's the situation of
Can I ask one
COVID-19?
Sorry?
How is the situation of COVID-19?
Not so good.
So good. The same.
Yeah.
You know, we have an Olympic.
Really?
Olympic in Tokyo.
Oh.
It's maybe 3 weeks later.
Are you going to visit?
No. No.
Thank you very much again.
So you are still having the Olympic instead of
Oh, hi.
Hi.
Pardon?
Thank you so much.
you are still having the Olympics instead of with even with all the protests. I mean, there are protests, right?
Yes, there are protests, and now we government discussing. I don't know. I don't know how to say. The people watching people, audience.
I think
Audience.
no audience.
Audience, no audience, maybe.
Yeah, it's pity. I mean, but Andre, in Russia, I see that things looks pretty normal in the lecture hall. Like you are without mask.
yes.
Yes. That's true.
We have some audience, yes.
It's very strange. In Osaka, our university also very normal, very normal. Yeah, but the hospitals, they say very serious.
Yes.
The hospital, they say very serious. But around the university, I don't see.
I see.
So how's the India?
India is terrible.
Delta type.
Now it has come down a bit, but I am afraid that it will go up again in a few months. Even though many of us has been vaccinated, but the vaccine, it is not clear whether the vaccine works, they can mutate or not.
Yes.
Thank you. 5 minutes. Thank you.
Thank you.
Thank you.
Который естественно, если его тоже... Нет, не хочу. Все четыре. Вот в этом месте 4. Который тоже разница. Да? Ну да. Ага. Я так когда вы писали, да, даже просто позицию просто может быть не так, вот это, мне кажется, да, он много гармоничный. Там вершины ставили, то есть красную точку. Похоже на все эти рассказки, когда в зависимости от вершины. Нет, результаты отсюда. Если то есть сознанием то есть там, ну, с одной стороны, это вот решение равнение Янки. Если я понимаю, что похоже, ну, соглашение. Так, вот, смотрите, результат он что утверждает? Он утверждает, что можно классифицировать с точностью до эквивалентности квантом. Что такое квантом? А квантом входит как раз решение равнения Янга-Макса, такое, что она становится неподвижной. Это неподвижность есть неподвижность. И кроме того, оно должно быть еще non-degenerate, не выраженное, свободно от квадрата. Если вот эти условия выполнены, то здесь взаимно однозначно соответствует. Вот это они почти одновременно написали работы, со стороны компьютера. И вот ввели, но Матвеев не называл термин квантов, кванты придумал просто. А Матвеев называл самым дефинитивным реактивным присутствием. Потому что там Квандл придумал, то есть он искал специально такое слово, которое ничего не означает. Это все везде доступно, то все равно всегда. Одна компонента следующего конкурса. Когда и там один здесь свои
понимаю, не умею.
Не, алгоритм-то есть. Смотри, построен алгоритм, который позволяет изучать эфир. Другое дело, что ну какой хотел бы более простой способ, вот квантовый, ну а квантовый тоже надо же проблемы геометризма.
Так, let's start to assume our next speaker is Krishnendu Gangapadhyay. Are you here? Okay. And the talk is reversibility of Hermitian isometries. Please. Please turn on your microphone. Your microphone is off.
Yeah, sorry. Okay. So thank you very much for inviting me to this talk. And it is a pleasure to meet many old friends again, though virtually. I am missing Tomsk this year, but we cannot do much. But anyway, something is better than nothing. So we are meeting virtually. All right. So can you, well, something is, so let me share again. Yeah, I hope it is visible. So the title of my lecture, as you can see, is Reversibility of Hermesian Isometries. Uh, I will say that it will be more sort of linear algebraic, but the theme fits into the broad area of group theory because the basic notions that we start with belongs to a group. So you start with an abstract group G, then an element small g is called real or reversible if there exists an H in G such that G and G inverse are conjugate by H. So essentially, if in a group capital G, two elements, an element is conjugate to its inverse, we call it real or reversible. And then if an element is of order 2, that is called an involution. And if an element is a product of two involutions in G, it is called strongly real or strongly reversible. Now, because of geometric motivation, some authors have also used the terminology bireflexionals for strongly reversible elements. Now, in this talk, I will flip between real and reversible from slide to slide, but keep in mind that the objects are same. So when I work with some algebraist collaborator, I call them real. And when I work on these objects from a geometric viewpoint, I call them reversible. But in this lecture, I will flip between the two terminologies. Now here is a quick observation. Suppose an element is a product of two involutions. Then it is conjugate to its inverse. The proof is very obvious. So every strongly real element is real. But what about the converse? The conversely, we can say that if G and G inverse are conjugated by an order 2 element, then it is a product of two involution. But when an element is conjugate to its inverse by an order 2 element is not in general a easy question to deal with. Now here is the broad theme of research that you take your favorite group G, classify real and strongly real elements, and suppose in your group G some element is not strongly real, then it is a natural question that how many minimum number of involutions one needs to express that element as a product of involutions. And then if you can do it for all elements over the bigger group G, you take their supremum of the involution length, that's called an involution length of the group G. So it is also an interesting problem to find out involution length of a group G. Now the notion of reality and strong reality or reversibility or strong reversibility appear from different perspectives and from different viewpoints, and they are pretty natural problem to study. So I recommend this book by Anthony G. O'Farrell and Ian Short, which published from London Mathematical Society in 2014 for a nice exposition of this problem from many viewpoints. So you can see that the motivation really comes from classical mechanics to classical finite group theory. But in spite of many works, a complete and concrete classification of real and strongly real element in a given group is known only for a very few families. Whatever satisfactory progress we have seen are for finite groups. So for example, I am not going to discuss here a survey of this work for finite group, but it's very interesting and there is a huge amount of literature. For example, in a famous work, Tiep and Zaliski, they classified finite quasi-simple groups where all elements are real. Now, several authors have investigated following this problem to classify many more families of real groups and many more groups where every element is strongly real. Now, I would particularly mention here that there is a group in Russia, especially in Novosibirsk, who have made significant progress in this direction about investigation of strong reality in finite groups. But my viewpoint is not finite group. I am interested in infinite groups, and for infinite group, mostly people have tried to find out the converse question, that when does a real element is strongly real. Now there are a series of work starting from 1960s due to the work of people like Ehlers, Unenberger, Djokovic, and so on, who have studied this question from a linear algebraic viewpoint over arbitrary fields, and they have sort of answered these questions for many classical groups. Now, most recently, one of the recent answer, as far as I know, was given by my colleague Anupam Singh and Manish Thakur in 2008, where they have found some condition for a connected adjoint for an element in a for a semisimple element in a connected adjoint semisimple algebraic group when it is I mean the equivalence between reality and strong reality for such an element. Now, this result I would not explain in detail, but a consequence of this result is that in most classical groups over a field of characteristic not 2, a semisimple element is real if and only if it is strongly real. Now, an exceptional class in this family is symplectic groups where still a complete classification is not known. And Singh and Thakur did not say much about unipotent elements. So that means the eigenvalue 1 elements in a group. And that is a question that we have investigated recently, but that's beyond the scope of this lecture. But recently we have classified unipotent real elements in a classical Lie group. Now, other than characterization of the type real if and only if strongly real, concrete classifications are known only for a very few families of group. So the question is that, can you list the real and strongly real elements in an infinite group to some way? I mean, can you classify them to some extent? I mean, the equivalence of real and strong reality is the one question, but to classify them or to list them concretely is another question, which I am interested in. Now, because of my title of the lecture, I think it would be first better if we recall the reversibility scenario in classical geometries. Now, we know that the classical geometries can be divided into 3 classes, spherical, Euclidean, hyperbolic. Now, let's start with the spherical case when the isometric group is the orthogonal group. Now, from the result of Unenberger, it follows that every element in orthogonal group, in fact, more generally, not only over real, and for me now the fields are only real and complex numbers, but more generally for orthogonal group over arbitrary field of characteristic not 2, Unenberger proved that every element is strongly every element is strongly real. So in the full orthogonal group in this setup, we know that every element is a product of 2 involutions, and you can choose those involutions when you are in a plane as reflections in a line. But when you go to the smaller group of determinant of 1 component, then this is not the case, and the situation becomes more tricky. Now, Nuppel and Nielsen, it follows from a work of Nuppel and Nielsen, a classification of real of strongly real elements in SON, that an element in SON is strongly real if and only if n is not equal to 2 mod 4, or if n equal to 2 mod 4, then there is an orthogonal decomposition of the underlying space into indecomposable subspaces, which should contain at least 1 odd dimensional summand. Now, one can also prove that an element in SON is real or reversible if and only if it is strongly reversible. Now, these two combined will give a complete classification of reversible and strongly reversible elements in SON. Now, as I have mentioned, that this group corresponds to the spherical space form, the automorphism isometric group of the sphere. Now we know complete classification of reversibility of isometries of a spherical space form. Now, what about Euclidean space form, which is the group when you take a semi-direct product of the orthogonal group with Rn? So this group, you can realize the action of this group on En by isometries of this form, x goes to ax plus b. Now, by looking at this action, how to classify reversible and strongly reversible elements in this group. Now, this question was addressed by Ian Short around 2008, where he proved that every element of the full group of isometries of En is strongly reversible. Now, what about the identity component or the orientation preserving isometries of the Euclidean n space, which is a semi-direct product of SON with Rn? Short also classified reversible elements, and in this group also, that first he proved that an element in the first he proved that an orientation preserving isometry of En of the Euclidean n space is reversible if and only if it is strongly reversible. And then he explicitly listed the strongly reversible elements. So if n is equivalent to 0 or 3 mod 4, then every element in the every orientation preserving isometry of En is strongly reversible inside this group. That means every orientation preserving isometry can be expressed as a product of two orientation preserving involutions of the Euclidean n space. And then when n equal to 1 mod 4 or n equal to 2 mod 4, the cases are much more finer, and accordingly you have to classify them. Short did that very successfully. Now this resolves the problem of classifying reversible elements of Euclidean space forms. Now what about reversibility in hyperbolic geometry? Now we will also have a complete answer in this setup, but for that let me first choose a model for the hyperbolic n space. So I take this matrix J, which express a n comma 1 quadratic form on R n plus 1, and then I defined O n comma 1 as the isometries which satisfy this quadratic form. In other words, it is the n plus 1 by n plus 1 matrices over real numbers satisfying this identity A transpose J, A is equal to J. Now this group preserves the n comma 1 bilinear form that I have already stated. Now a model of the hyperbolic n space is the conic given by vectors of length -1 under this bilinear form. Now that conic has two components. We choose one of the components, the component where x0 is positive, as our model for the hyperbolic n space. So this is a linear model for the hyperbolic n space, and we can realize our hyperbolic isometries as linear transformation. So you can do linear algebra. Now there is a metric which you can define as dx comma y. So that is essentially cosine inverse of minus of this inner product. But that metric is not directly involved in our setup, but that metric is giving me one of the four components of On comma 1 as orientation preserving isometries of the hyperbolic n space, and two of the components of On comma 1 as the full group of isometries of Hn. So those components which preserves Hn. Now we denote that full group of isometries of the hyperbolic n space by POn comma 1, and it's a classical result, and it follows from several works. Like Unenberger, Short also proved it, and one of my previous work also, it follows that every element in POn comma 1 is a product of two involutions. So it's more or less like our previous Euclidean setup. But again, what about strong reversibility or reversibility in the identity component of the isometric group? That means of the orientation preserving isometries in the group of orientation preserving isometries. All right, so that's the question which requires finer analysis. But now here, first, before stating that result, I will briefly recall the case n equal to 2. So in that case, you can realize, it's well known that you can realize SO not 2 comma 1, which is the identity component of either O2 comma 1 or PO2 comma 1. You can identify it as this group SL2R mod plus minus identity. Now, this identification is done by the action of SL2R on the hyperbolic 2 space, and the action is in terms of Mobius transformations. Z goes to AZ plus B by CS plus D. Now, as soon as you do that, you can easily see that the translation Z goes to Z plus 1 is not conjugate to Z goes to Z minus 1. Because you look at the dynamics of the translation on the boundary, on the real line. Now, the orientations of the translations are different. So orientations of T and T inverse are different, so they cannot be conjugate to each other. So this is a simple proof of this result. So that means in SO not 2 comma 1, not every element is real, or so not every element is strongly real. Now SO not 3 comma 1, you can identify it again by Mobius transformation with the Riemann sphere. You can extend the whole thing to hyperbolic 3 space. Now it's a classical result of Frenchel that every element in SO not 3 comma 1 is a product of two involutions. So you can find it in the classical book by Frenchel on hyperbolic geometry. Now this shows that the reality and strong reality can be very different in different dimensions of a geometric space and in different subgroups of the same group. So even if you know reversibility and strong reversibility in a bigger group, it is always a valid question that you look for a smaller group of importance and ask the same question. Now for SO not n comma 1, I classified the reversible and strongly reversible elements in 2011. So like the Euclidean case, every element in SO not n comma 1 is real if and only if n is either 0 mod 4, that means n is either of the form 4k or 4k plus 3. Now, when n is of the form 4k plus 1, an element in SO not n comma 1 is real in SO not n comma 1, if and only if either it is an element with no eigenvalue lambda, such that mod lambda greater than 1, or if it is such an element, then it must have an eigenvalue plus 1 or minus 1. So that means, in other words, the elliptic and parabolic elements, they are all real or reversible. Now, when n equal to 2 mod 4, even then you can classify them completely. So an element is reversible or real if and only if either 1 or 2 above holds with plus 1 omitted from the statement, and if it is of the form 2 but without an eigenvalue minus 1. All right, then you must have an eigenvector to 1 such that the eigenvector has norm positive. This is the linear algebraic classification of the real elements in SO not n comma 1. Now I must note here that independent of this work, around the same time Ian Short also proved a version of this result, but he took the ball model of the hyperbolic n space and he gave a more geometric classification, but essentially that is equivalent to what I am saying here. All right. Now this was the classification of real element. Now it is not difficult to prove that an element SO not, an element in SO not n comma 1 is real if and only if strongly real. So these two theorems together classify strongly real elements. Now this essentially completes the picture of classical space form of constant curvature. I mean the question of reversibility and strongly reversibility in the classical space form of constant curvature. Now one can also ask more general questions, like you have this rank 1 symmetric spaces. So there are complex and quaternionic hyperbolic spaces. Now what about the question of classifying reversibility and strongly reversibility for complex and quaternionic hyperbolic isometries? So now in 2013, in a joint work with John Parker, we classified reversible and strongly reversible elements in this group ACU n,1, which acts as isometries of the complex hyperbolic n space. And in recently last year, in a joint work with Sushil Bhunia, we classified reversible and strongly reversible elements in this group SPn,1, which is the quaternionic analog of UN,1 and is the isometric group of the quaternionic hyperbolic n space. Now, when you go from complex to quaternion, it is not always easy, as we will discuss shortly. So now this completes the picture of the reversibility in the classical hyperbolic geometries or classical space form geometries. Now, in the rest of the 10 minutes of my talk, I will discuss a more recent development where we have asked the question for Hermesian isometries. I will tell you immediately what are Hermesian isometries. But before I proceed, I must say that this is a joint work with my student Tejbir Lohan at Aysar Mohali. So let's start with considering the underlying not field, but the skew field as complex numbers or the division ring of quaternions. Now consider the n-dimensional vector space over F and equate it with the positive definite F Hermitian form. Now the unitary group is the group which preserves this Hermitian form. Now in matrix notation, these are n by n matrices over complex or quaternionic numbers, which satisfies G bar transpose G is identity. Usual notations, when over complex numbers, we denote it by UN. When over quaternions, we denote it by SPN. And these are compact subgroup of the general linear group. All right. Now, Hermitian isometries. So before that, let me quickly recall what are the quaternions. The quaternions are four-dimensional division algebra over real numbers. You can think of them as a division algebra spanned by four numbers, 1, I, J, K, where the numbers I, J, K satisfies these identities. So these are essentially generalization of complex numbers in dimension 4. And it's a classical result that these are all real division algebras over real division associative algebras over real numbers. Okay, but this is the quaternions. But one key point here is that the quaternions are non-commutative because I and J don't commute to each other. Accordingly, not every element commutes. Okay. And you take a so when we take a vector space over a non-commutative space, we have to specify the multiplication whether from left or right. So here I am taking a right vector space over quaternions. Now given a right linear map, one can represent it by a matrix over the quaternions, and that's what we are doing here. However, whatever linear algebra we do does not carry over from complex number to quaternions for the reason that you take any element non-zero quaternion lambda and take a vector v from capital V such that it's an lambda is a right eigenvalue of a linear transformation T. Then you can see that, as I have showed in the slide, that V mu is also an eigenvector, but not corresponding to the eigenvalue lambda, but corresponding to the eigenvalue mu inverse lambda mu. So when we are over complex number, these commutes and mu inverse mu cancelled. So we get a corresponding to a eigenvalue, we get a whole one-dimensional subspace spanned by an eigenvector. But here, corresponding to a one-dimensional subspace spanned by an eigenvector, we don't have one single eigenvalue, but we have a similarity class of eigenvalue. So the eigenvalues of a quaternionic linear transformation occur in similarity classes. So so that's something that increases the the complexity of the linear algebra over quaternions. Now you give a metric on V, which is the usual metric. Now the metric is an affine metric, right? So the isometries of the given metric are of the form x goes to ax plus b. So these are quaternionic and Hermitian analog of the classical Euclidean isometries. And the isometric group of V comma D, this metric space, is the semi-direct product of the unitary group over F with Fn. Now our problem is to classify reversible and strongly reversible elements in these groups. Now this would generalize Short's result in this setup. Now here is a recent result that we have proved that you take one isometry of Fn under of the Hermitian space. So that means I express one element in this semi-direct product as a pair where we have a linear part and we have a translational part B. Then the result is that in a joint work with Tejbir, we have proved that this element, such an element G, is strongly reversible in this group if and only if the linear part is also strongly reversible. All right. Now, what about reversibility? We have been able to prove that every element in SPN semi-direct product, the n-dimensional quaternion space Hn, is reversible. So there is no ambiguity. So every element is reversible there. And strongly reversibility means if the linear part is strongly reversible, then the element is strongly reversible. But over complex number, not every element is strongly reversible. We have been able to prove that an element G in UN semi-direct product Cn is reversible if and only if it is strongly reversible. All right. So this is the result. So not every element in UN semi-direct product Cn is reversible. Yeah. So this is the result that we have shown. And in a previous work with Sushil Bhunia, we have classified reversible elements in SPN, and in a joint work with John Parker, we have classified reversible element in UN. So combining all together, you have a concrete list of reversible and strongly reversible element in UN semi-direct product, UNF semi-direct product Fn. But now, as usual, we always love to look at a smaller and more natural group, which is the group SU4, C semi-direct product. So you replace UN in the complex case by SUN, the determinant 1 matrices. Now, what is the scenario there? So now I don't have much time. I have only 3 minutes, so I shall be able to discuss one example only. So you take an element in SU4 semi-direct product C4. Now take this matrix A, which I can express by e to the power I diagonal element, e to the power I theta, e to the power minus I theta 1, 1, and choose the vector V as this vector. Now, by our previous work, I mean, these sort of matrices are reversible in SUN. All right. I mean, in fact, they are strongly reversible there. Now here, if possible, that this element G is strongly reversible in SU4, C semi-direct product C4. Then there exists an element H, which is of the form B, U, which will conjugate it to its inverse, and square will be identity. In particular, A and A inverse will be conjugated, and you can write B in this block form B1, B2, where B1 is this off-diagonal matrix AB, where A, B are non-zero complex numbers, and B2 is an arbitrary matrix in GL2C. Now, so now from the equations H inverse equal to G inverse and H square equal to identity, you can see that for all X in C4, these identities are satisfied. All right, so which would imply BA B inverse equal to A inverse, and A inverse minus identity will map V minus U to B plus identity into V. Now apply B square equal to identity, you will get B plus I into U. B plus I applied to U is equal to 0. Now these three equations, if you look them carefully, that would give you the B2, this second block, as minus identity, and AB equal to 1. So my B will be of this form. So determinant of such a B is -1, and hence B does not belong to SU4. So the assumption that we start with, that if possible, suppose G is strongly reversible, cannot be hold, because by following our relations, we end up in a matrix which is of determinant -1. So A is not strongly reversible in SU4 semi-direct product C4. So this shows that the result that I have stated here, the theorem, the first theorem, that an element in the semi-direct product is strongly reversible if and only if its linear part is strongly reversible. That does not hold for when you restrict yourself to this group SU4, C semi-direct product C4. And when you go from 4 to the n, then essentially this example generalizes. Okay, and up to conjugacy, we have done that. We have classified the classified the elements which are not strongly reversible in SUN, C semi-direct product Cn, and the prototype to this is this example. And here is the theorem that you take an element in SUN, C semi-direct product Cn. Suppose it is up to conjugacy is of this form, just like what we did in the example, we are generalizing that. Then the following are equivalent. G is not strongly reversible if and only if this vector VL, this non-zero vector VL, are all non-zero for L equal to k plus 1 to n. And one of the following holds, that either n is even and k is odd, or n is odd and k is even. All right. And the proof essentially is a generalization of the previous analysis for SU4, C semi-direct product Cn. So if we carefully study that example, the general proof will just follow you in the same sort of argument. Now with this, I will stop my lecture here. Thank you very much. Spasiba for your attention. Now, this is as I told you that I am missing Tomsk. Now, long back in 1 BC, before Christ, normally BC means before Christ, but now I count BC as before COVID-19. So in 2019, this is a photo from 2019. So this is a photo on 24th June, 1 BC, 1 year before COVID-19 pandemic begins. I hope we will soon come to AD and I will visit here again. Thank you.
Okay, thank you.
Any questions?
May I ask one question?
Okay.
Yes.
Yeah.
Yeah, Krishnendu, thanks for the talk. Nice talk, in fact.
Yeah.
So I have a question, maybe rather not appropriate, but over real, right? And I think reason for considering them is the geometric and topological reasons. So I'm just wondering whether this reversibility has been studied over matrix groups, over other fields, which are of number theoretic interest.
Yes. It has been studied. So for example, if you take the group SL2Z, okay, so 2 by 2 matrices over the modular group. I mean, that's one of the most important group for number theoretic interest, right? So reversibility has been studied there, and it's a very difficult problem. So classifying reversible element in SL2Z is a very difficult problem, and
like for
people
example,
have not known. So over SL2Z itself, it is a very difficult problem. Okay, so you need very hard combinatorics to solve that problem. And there are also, arguments using classical dynamics, dynamics from the torus, where people have classified reversible elements. So it's a good question, but it's a very hard problem.
Further questions?
Thank you.
Yeah.
Hi, Krishna.
Hi.
Thank you for interesting talk. I would like to ask about involuntary length in your group of isometry. You study group of isometry, in which group involuntary length is equal to, and what is the large involuntary length?
Well, I mean, that's a it is known for the groups SO n comma 1, it is known. It is, I think, 3 there. It is a work of Musket and
Sorry,
Basmatian.
in which group? You
Yeah.
say in some group it's known. In which group it's known?
The orientation preserving isometric group of the real hyperbolic n space, SOn comma 1.
SO.
Yeah. SOn comma 1, it is known. It's a work of Ara Basmajian and Bernard Musket. So they published a paper in the Transactions in 2011, where they have computed the involution length in these groups. Now for SU2 comma 1, it is known. That's again a difficult problem. So for SU2 comma 1, it is 4. It's a work of Pierre Will and Julian Poppert. And for SUN comma 1, they have argued that it is at most 8, but they have not proved exactly how much it is. All right.
You know the larger element of length 8.
Yeah, there is no larger element of involution length 8 in SU.
Yes.
Yeah. For other groups, I don't know. For SPN, the compact groups, we know something. For like ON, it's well understood. For UN, SUN, we know. For SPN also, I know that there can be at most, the length can be at most 5. But for this rank 1 groups, except SON comma 1 and SU2 comma 1, it is not precisely known. Yeah.
More questions? Nice. So let us thank the speaker again.
Thank you very much.
Так, ну теперь у нас фотография. Да? Yeah, so this session is over, and now we will make picture.
Нет.
So thank you very much.
Thank you. Bye-bye.
How is Kakoli?
Kakoli is fine.
How is Tim and your baby?
Yeah, Tim is also good. How are you?
Oh, I am fine. Okay. Say hello from me.
Oh, sure. I hope that we will see each other in person again in a year or 2, maybe.
Okay.
Yeah.
Thank you.
Okay. Bye-bye.
Фотографироваться. Так, а там перерыв же.